Okay, so this is going to be shear example 5 continued. So I won't draw it really thin, but it's actually meant to be intended to be thin, but I'll just draw it looking a bit thicker, so that we can clearly show the arrows. So just put here thickness not to scale. Now we want to be making a cut. So let's say, for example, we're going to make our first cut here. So we do a cut there, and we want to work out what the shear flow is at the position of the cut. So we do what we always do. We're going to use the same equation as before. 2, 1, 2. So that line is going to be the neutral axis. So we've made our cut, and we've got the equation that the shear flow, and the shear flow is going to be equal to the shear force, which is going to be 10 kilonewtons, multiplied by S dash of wherever we are calculating it, so it's a function of y, and we're going to be dividing that by I. Now in this case here, if we wanted to work out the shear stress, we would be using the thickness. We would be using the thickness of the section. And remember that the units of the shear flow are in, let's just say it would be in newtons per millimeter. So you would be getting a unit in terms of newton per millimeter, and we've already made the assumption that the thickness is going to be really thin, so that T is very small, because it's I should say capital T is very small, because it's a thin wall. Because we're assuming that it's a thin walled section, and so the transverse shear stresses disappear. So what we need to do is, if we wanted to work out the shear flow, we would use the same equation as before, and we would just shade the bit that we want to calculate. We could, of course, shade the rest of the section instead, but that would be a more involved calculation, but you would get exactly the same answer. So if I haven't explained that right, let's if you took out the section again, not to scale, we're going to be making a cut here, and that's going to be our neutral axis. If you had considered all that, it should work out to be the same. So to work out the equation for the shear flow at that cut, to be calculating the section properties. So we're going to be calculating the area and using the dimensions. So that would be equal to V times S dash, which is going V over I, which we've assumed you've calculated, multiplied all that by S dash of the shaded area. So maybe I should put in brackets shaded area and S of the shaded area, about the neutral axis. So we would now want to work out the area. So if that dimension is going to be B, and if that is going to be t, that distance here is going to be b minus t over 2. So that dimension there is b minus t divided by 2. So we'll put b minus t over 2 as the first bit, and now if we wanted to work out the thickness, we know the thickness is going to be t, so that needs to be multiplied by t, so that would give us the area of shaded portion. And then we would need to multiply that by the distance of the center. So if we are going to know that that distance there is big D, so that is going to be big D, just small d. So that distance there is going to be d over 2 minus t, and then that distance to the center that d over t is going to be up to there, and then the distance to there is also going to be t over 2. So then we would get the distance from there to there is d over 2 minus t plus t over 2. So that was d over 2 minus t over 2, minus t plus t over 2, and that is going to be d over 2 minus t over 2, which is then going to be equal to d minus t over 2. So we'll be multiplying that by d minus t, all divided by 2. So that would be the equation for making a cut there, and it should be obvious that if we repeated the exercise and we did the cut, so just try to draw that out again. It should be obvious that if we now did the cut here instead, for the cut there, make a cut there, that if we had used that shaded area, we would also get the same equation. So Q, so we'll call that the first cut, we'll call that the second cut. Q of the first cut, Q1, would be equal to Q of the second cut, and that is V over I times B minus T over 2 times by T times by D minus T over 2. So that would give you the shear flow at the second cut. And if you want to tell me that they're actually in the opposite directions, that's fine. Just pretend there's a modular sign on both, and that should sort it out. And incidentally, that shear is also going to be the same if you did cuts at those portions instead.